Module 13D, we're going to start getting into our crystal structures, so our cubic structures. In this module, I need to be able to compare and contrast the structures of the three types of cubic lattices. That is a simple cubic, body-centered cubic, and face-centered cubic. You should be able to predict ionic empirical formulas by analyzing its unit cell, calculate the density or atomic radius of a metallic element giving its cubic crystal structure, simple cubic, face-centered cubic, or body-centered cubic, and memorize and apply the equation for edge length of a unit cell and the number of atoms per unit cell. You need to be able to have this done so that you can do this. So the three types of cells that we're going to look at, cubic cells specifically, is simple cubic, face-centered cubic, and body-centered cubic. A simple cubic, you have particles at the 8 corners of the tube, or of the cube. There's total of 1 particle per unit cell. Each corner is shared with 8 different atoms. So overall, we may have 8 corners, but each corner is shared by 8 different things, so it each contributes overall 1/8 to the overall structure, so 1 particle in total per unit cell. For a body-centered cubic, it's just like a simple cubic, except we also, in addition to having 1 particle at each corner, we have 1 particle in the center of the cube. This gives me a total of 2 particles per unit cell. In face-centered cubic, it's a simple cubic with 1 particle at every corner. In addition, it also has 1 particle centered at the side of each cube, in the face, where it's shared between 2 different unit cells. So a total of 4 particles per unit cell. So looking at a simple cubic lattice, this is what a simple cubic would look like, just a particle at each corner. And each corner is shared 1/8 of the atom in 8 corners. 8 corners, 1/8 of a particle at those 8 corners, total of 1 particle per unit cell. So simple cubic, 1 particle per unit cell. Each one of these circles is shared. If you built this out and actually put blocks together, you would see that each corner is touching 8 different unit cells. So each one contributes 1/8. Since there's 8 of them overall, we say that it has an overall 1 atom per unit cell. This is the equation to calculate its length. Its length is equal to 2 times the radius of one of those particles, so 2r. Simple cubic, 2r is your length. Body-centered cubic, we have that 1/8 of a particle at the 8 corners of a cube, just like our simple. So each of these circles are shared by 8 different things, so they each contribute 1/8 to this unit cell. But we also have 1 particle, this orange one we see in the center, centered inside the center of that cube. So that one in the center is only residing within this unit cell. That gives me a total of 2 particles per unit cell. Because this one was not being shared by anything else, it's completely unique to this unit cell. That is called a body-centered cubic cell. We see it here as well, where it's centered inside the body. So BCC, 2 atoms per unit cell. You can go through this math if you would like to, but otherwise this highlighted in green is what you need to know. The length is equal to 4r divided by the square root of 3. So body-centered cubic, 4r divided by the square root of 3. And a face-centered cubic, just like simple cubic and body-centered, has that 1/8 of a particle at the 8 corners of the tube, but it also has 1 particle at the center of each face. So we see, it's harder to see in here, but each one of these are a face. So it's shared half with this unit cell, half with the unit cell that it's attached to. We have 6 faces. Each face is shared half with this molecule. So that's a total of 3 atoms due to the faces. So a total of 4 particles per unit cell. Hence the 1/2 times 6. 6 faces. 1 down here, 1 back here, and 1 behind. 6 faces, each contributes 1/2, overall 4 atoms per unit cell. And again, you can go through the math if you would like to, but L is equal to 4r divided by the square root of 2. This is what you'll need to know to be able to do calculations. We also have like cubic close packed and extended structures we see here. So for a face-centered cubic, we can see the way these are packing on each other. You can pack them so that they maximize space or they minimize space. And it's hard to see on here, but the way it's being built apart is like, or built on each other, is like this blue is hitting right here in the spaces of the molecule. So it's considered a cubic closest packed. It's not leaving any empty space. Anytime there's like a space inside of here, that's where this blue atom will fit into play. A blue atom will fit into play. Blue atom will fit into play. We can also have them where they're not closest packed, so basically it's kind of like, what I mean by this is if I've got a structure like this, the next one on top would pack in these holes. And then this would go on top here. And I know these are not spheres, but the other way you can do it is where they literally land right on top of each other. And that leaves more space in between the structure. Your structure summary, coordination number, I forgot that part. Coordination number here is 12. Coordination number is the number of touching atoms that we have. So how many atoms is it actually touching? Corners shared by 8 unit cells, so 1/8 atom each. Edges shared by 4 unit cells, 1/4 atom each. Faces shared by 2 unit cells, 1/2 atom each. A body is in 1 atom only, it doesn't share at all. And the coordination number is the number of touching atoms. We didn't talk about edges, so we didn't see them in there, but you could have edges, and we'll see that in a structure in a minute. But what I mean by these things is your corners, your edges would be along your edges here. Your faces and body centered are hard to draw. Faces would be shared between 2 atoms, and body center would be directly in that atom. So calculate the empirical formula for each of the following unit cells. How do I do this? What I do is I look at this and I see, where do these things reside? Are they in the corner? Are they in a face? Are they in the center, meaning the body? Are they at an edge? And then how many do I have of each thing? So when I look at this one, I'm going to look at the first one, the green purple. I'm going to look at the greens. I've got green, 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 green. Those are all edges. Green, 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 green. Edges. Green, 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 green. Edges. So I've got, for my green, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 edges. An edge is shared by 4 different unit cells. So I'm going to multiply that by 1/4. That gives me 3. But I also have one more in the very center that's not in an edge at all. It's actually in the center. So like a body. Overall, that gives me 4 green. Now I'm going to do the same thing with the purple. If I look at my purple, 1, 2, 3, 4, 5, 6, 7, 8. I've got 8 corners. And it's hard to see these, but these are faces. 1, 2, 3, 4, 5, 6 faces. How do I know they're faces? Well, a couple reasons. The easiest of which, well, there's 6 of them. But the easiest one for me to see is right here. I can see that this is definitely at the face. This one I can kind of tell it's at the face, but this one on top I can really tell it's at the face. And there's 6 of them, so that means I've got 6 faces. So for purple, I've got 8 corners. Corners contribute 1/8, so that gives me 1. I've got 6 faces, and faces contribute 1/2, so that gives me 3. So overall, I have 4 green, I have 4 purple. My formula here would be, my empirical formula would be GP, green, purple. 1 green to 1 purple for my overall formula, because I have 4 green to 4 purple. Let's do the red and green one. If I look here, I've got 1, 2, 3, 4, 5, 6. It's hard to see, but I've probably got 7 and 8. I can see the corners. So I'm going to say I have 8 corners for the red. Each corner is 1/8, so overall 1. So I may not always be able to see all the pieces, but I can deviate from that, saying, okay, I see 1, 2, 3, 4, 5, 6. 7th one's right there. I can pretty much say, yeah, there's going to be 8 of them then. Okay. The other thing I see though is that there's red here, red here. You can see a red here. That means I've also got red on my faces. There's going to be 6 faces per unit cell. So overall 3. Meaning I have in this compound, I have 4 red. Next, I'm going to look at my green. I see the green here, here, here. These are edges. I've got 12 edges. Each edge contributes 1/4, which is an overall 3. And I know it's really hard to see here, and I would try to make this more clear and easy to see on an exam or a quiz, but there's one inside of here. There's a body. So I have 4 green, which means my overall formula here would be RG, 1 red to 1 green, my empirical formula. When I look at this one here, we'll call this red-blue. When I look at my red, I see red at all of my corners. So I've got 8 corners. I also see that I have red at my faces. So I have 4 red. Look at my blue. I've got blues, but they're all bodies. I have 8 bodies, and each body contributes 1. R4, B8 is simplified down to RB2. And the last one, the pink blue over here, I've got 8 blue at my corners times 1/8 gives me 1. I've got 1 pink body, gives me 1. So blue, pink, or BP. You should be able to go through these and count these up and figure out what is your empirical formula based on these structures. Again, I know this one's really hard to see. If it was on a quiz or exam, I'd give you one that's a little bit easier to see, like these other 3. But you should be able to see these structures and figure out their empirical formulas. Zinc sulfide crystallizes in the unit cell shown below. How many formula units are found within this cell? How many repeating units do I see? When I look here, I'm like, wait a minute, I definitely see repeating units. Overall, you should be able to see 4 repeating units, with the zinc centered in each repeating unit. The zinc is inside your body, or inside the body of the structure. So I have 4 formula units within this unit cell. Silver has a face-centered cubic structure as a solid. Assuming that silver has an atomic radius of 144 picometer, calculate the density of silver solid. Or solid silver, whatever we want to say that. Okay. Face-centered cubic, FCC. FCC has 8 corners times 1/8, so 1 atom. 6 faces times 1/2, so 3 atoms. Overall, 4 atoms per cell. That is not drawn very well. We'll pretend. Your corners and your faces. We know the atomic radius. Is 144 picometer. We're trying to find density, and density is your grams per centimeter cubed. So the grams of your cell divided by the volume of your cell. How can I find the grams of the cell? How many grams per cell do I have? Well, I know that silver, if I look at the table, silver has an atomic mass of 107.87 grams per mole. I know that Avogadro tells me that that means I have 1 mole. For every 1 mole of silver, I have 6.022 times 10 to the 23rd silver atoms. This is FCC, which tells me I have 4 atoms per cell. That gives me grams per cell. 7.165 times 10 to the minus 22nd grams per cell. So I've got this portion. Now I just need my volume per cell. Well, I know that face-centered cubic. I know my volume is equal to my length cubed because it's a cube, right? But my length is equal to 4r over the square root of 2 because I have a face-centered cubic. So my volume of my unit cell will be 4r over the square root of 2 cubed. I do want this in centimeters though, because density for solids is going to be reported in grams per centimeter cubed. R, 144 picometer. I want to convert this to centimeter. I know 1 meter is 10 to the 12th picometer. And 10 to the 2nd centimeters is 1 meter. 1.44 times 10 to the minus 8th centimeters. Plug this in for R. I get a volume of 6.757 times 10 to the minus 23rd centimeters cubed per cell. Now I've got my bottom half. Now I can go ahead and just calculate my density. 7.165 times 10 to the minus 22nd grams per cell, divided by 6.57 times 10 to the minus 23rd centimeters cubed per cell. And of course I ran out of space writing down here. Gives me 10.60 grams per centimeter cubed. There you go. 10.60 grams per centimeter cubed, the density of silver. And if you look it up, you should find that it's pretty similar to your answers here. You should find very accurate calculations. How about this? A compound forms a crystal structure with cations M at each corner and on each face. 8 anions occupy the holes in the structure. What is the formula of the compound? For me, you can do this however you want. For me, the easiest thing to do is to draw this out. So I've got crystal structure. We'll pretend that's straight. And it says cations M at each corner and on each face. M is just a way we often represent a cation. It's just a generic letter for it because M stands for metal and mostly cations are metals. It's telling me I have one at each corner. And each face. I have 8 corners. Times 1/8. 6 faces. Times 1/2. So M4. I have 8 anions in the holes in the structure. Simplify that down for empirical formula. M2x4, nope, not simplified enough. MX2, yep, that's it. The formula will be MX2. Okay, so work through these, see if you can try to understand what these things mean, how they're put together. Look at the additional practice for more practice problems on this, but you do need to be comfortable with these calculations.